So first, any questions? So I did have somebody approach me in the hallway as I was coming in. Apparently I never made it available to you the next homework and quizzes. They're up there. At least I think they're up there. Maybe up there for last semester, but I put them in the wrong BB Learn section. So I will double check that. I apologize. My life, as you know, because what I said last time, life's been kind of crazy. And so I probably just put them in the wrong place or didn't turn them on. I'll get them there. There'll be a lot up there in terms of quizzes and homeworks to make up for what we're missing. I'm going to be very flexible on the due dates. I want you need to get the points because that's what we have there, but I want to be a little more flexible on when you get those points because you probably have midterms and other things right about now and other classes. So I'll be flexible. All right. What I wanted to talk about today was networking. Now, the concept of networking is that I'm going to have a computer here. Okay, let me see if that lets me draw. There we go. Boy, that's an ugly computer. Okay, so I have a computer here with a little keyboard. I'm not going to try and be fancy. Okay, and it wants to talk to a computer over here. There are many things we have to worry about when the two computers are talking to each other. Number one is how even do they talk? How do I send the letter A from computer one to computer two? Or let's go back to our crypto section. Computer Alice talking to computer Bob. Okay, how does Alice send a single character to Bob? So there are what we call standards out there, different standards that define how we propagate this information. You may have heard of one of them called the, whoops, let me fix that. 802.11, that is the Wi-Fi standard. And 802.11 is just the name of the numbering of the standard from the International Standard Organization. And it talks about things like what frequency we're using. Is it a 2.4 gigahertz, a 5.0 gigahertz, megahertz, whatever the different frequencies of communication. What do they mean? How do they transfer? There's other standards out there. Ethernet, you've heard of Ethernet, right? I've got an Ethernet cable plugged in. Well, there's a standard about that. How many pins are there? What size of the plug? Which pin is power? Which is ground? Which ones transmit? Which ones receive, etc. What does it mean? How do you get let me get a 1 and a 0 between the two computers. If I can send you ones and zeros, I can build that up to letters, I can build that up to messages, I can build it up to anything, but how do I get a 1 and 0? Well, maybe a high voltage is a 1, a low voltage is a 0. Okay, so well, what if I want to send a bunch of ones? That's a bunch of high voltages. You're going to look and you see, well, it's constant high voltage. How many ones is that? So there's a timing and a signaling. And some of the protocols out there say, well, actually, what we're going to do is we're going to transition from high to low or low to high, and that'll be a 1 to 0. We're always going to go from high to low, back to low, and then back up, or whatever. Well, it'll be Cyber 330 by the time you get to it. CS 420 now. It talks about that type of stuff. We're not going to go into it in detail. But the fact is, that's just the first thing we have to do. How do we get ones and zeros between these computers? Things get worse. Things we have to deal with. So I will get rid of all that writing. Oh, I lost Alice and Bob. Well, we got Alice, Bob, and let's say Eve here, all on a network, and they're all communicating via Wi-Fi with this Wi-Fi, what we call an access point. So Wi-Fi access point. Alice wants to send a message to Bob. How do we know Eve doesn't get it? How do we get the message just between Alice and Bob?
To have a direct connection between two.
Well, there's a Wi-Fi, no direct connection, right? That gets to be the problem. Or the old wiring, we all shared wires. Now it could be, let's go to direct connection. It could be these are direct connections and we have a switch here. when everybody's plugged into it, switch has to know, hey, I'm sending this to Bob instead of to Eve, right? And so we have to have a way of identifying each device. And if a device has multiple network cards and we have multiple plugs, we have to identify which plug in that device. So there are standards about that. One of the things we have is called a MAC. Now, this is like a MAC address on a network card. Media access control, not mandatory access control like we saw on crypto protocol, or oh wait, we haven't covered that yet. That'll be next chapter. But this is media access control. It's a unique number for every single device on the network. Every single network card has a unique MAC address. And it's something like 50, and then you see a colon, 50 colon A3 colon 00 colon 11 colon FE colon colon C2, whatever. The first several of those are actually unique per company. So if I have a Linksys network card, it'll be a Linksys number. If I have a Cisco card, it'll be a different Cisco number. And then the last four are unique to that card. So that we can know, that switch knows, oh, Alice is talking to Bob at that card. Well, how does Alice know what MAC address to use for Bob? So there's protocols about that. We'll go into that later. That only works if we're on the same connection, the same wire, the same network. Then I can directly direct it to another machine using its MAC address. Wi-Fi uses that, et cetera, if we're on in the same room, the same access, the same network. But I want to go even beyond my local network. I want to talk to people who are on a different local network, say at WSU or over at Amazon or somewhere in Europe. They have their own local networks where they're talking to each other, but I want to talk to them over there. To do that, we need what we call internetworking, where we connect multiple networks together. Like intramural sports, it's within a single organization, a single network. Internetwork, intramural sports, it's between different networks and groups. So the internet allows you to go and talk there. Well, we need a different way of doing that. One, when they were doing this, Ethernet, I was talking those MAC addresses, well, those MAC addresses are Ethernet MAC addresses. If we're not using an Ethernet protocol, and Wi-Fi shares that, we're using some other type of network, it may have different numbering. And so we need a common numbering scheme. So they invented what they call the Internet Protocol, where we gave this common numbering scheme. We'll go into that. People are lousy at numbers, right? So the machine in my office, I'm making this up, this isn't the real number, is its internet address is 129.101.100.1. How about Jim's computer at uidaho.edu? That'd be easier for me to remember. And so after going through this idea of numbering, they said, let's start doing namings. So when you want to go to Google, you don't have to go, oh shoot, what is the address Google uses? I just go google.com. Right, and so let me stop that share, and actually,
MAC address is less security now when it comes to security to like base information sending off of, because they can be spoofed.
Everything can be spoofed. We'll get to that. Oh, that's not. Wrong command. Okay, there we go. I better share the screen so that everybody sees this. So there's a program called Name Service Lookup, NS Lookup. And if I go www.google.com, it says, hey, its number is 142.250.217.68. Well, there's a system out there, a protocol called Domain Name Services, where I basically ask my local gateway, my local name server actually, hey, I don't know anything about Google. Where are they? Who are they? And I said, well, I don't know. I'm going to ask the more centralized person. It goes up with this hierarchy until it finds an authoritative name server who says, hey, yeah, I know about Google because I'm the Google parent. www.google.com is this number. And then it sends it back down. This also has some security issues we can deal with, but so the whole idea here is we have mechanisms, we have ways of communicating, people to put this together. Now, I'm going to go over some details of this. Some of this will be horribly boring to you. Some of this will be horribly confusing to you. That's okay. Okay, maybe not the boring part, but the confusing part's okay, because there's a lot there. People have been, building this stuff up since the 60s. Okay, where a lot of the protocols came out in the 70s and 80s. The Internet Protocol, the formal version, I think is 81, the standard for that. The numbering I showed you, this 129.101.100. Whatever, that's Internet Protocol version 4, which rolled out in the middle of the 1980s. They shut down the whole internet for 2 days, and everybody installed the Internet Protocol 4 stuff. In the mid-90s, they came out with version 6. Not everybody still uses that because we're never able again to shut down the whole internet for a couple of days to do a patch. Why did that? Internet Protocol 4 has 32 bits. 32 bits is 4 billion. There's 4 billion unique numbers for internet devices in the world. Well, we've got a lot more than 4 billion internet devices now. We ran out of numbers a long time ago. We've done tricks and tricks like crazy. I have 10 devices in my office using a single Internet Protocol number. Okay, and there's lots of ways we do this to kind of fake the system. IPv6 has 128-bit numbers, so there's a unique number for every molecule in the galaxy, so we'll be good for a little while. But it takes forever to roll out, and people are still working on that. But yeah, I remember them shutting down the internet for the couple of days to roll out IPv4. I had a homework assignment. It was really interesting. Anyway, okay, let me talk about this stuff. So there's a whole lot here, and there's security implications to this. And part of the security implication, okay, this is looking weird. Well, that works. Part of the security implications we have is that people design these planning to share. I mentioned IPv4 with 4 billion unique addresses. I was at a conference where somebody was talking about the original Internet Protocol when they were originally rolling this out and setting up the network. And he says he was in a meeting and somebody was saying, yeah, I'm going to be bold. I think someday we may have up to 256 unique sites on the internet. And we got to be ready for that. At that time, they had a dozen. They're like, I don't know, because it was a couple military bases, a couple research universities. They're like, I think this is going to be bigger than that. And even then, when there's files on your computer, what they call networks file and a host file. Network file lists all the different unique networks you know about. Host files lists all the different computers you know about. When I was a college student, I could look at the networks file and say, oh, there's UC Berkeley. And then I could look at all the main computers at UC Berkeley. You could UCLA, and I was at UC Davis. And I could look at these different ones and see everyone. And that's before they shut it all down. So we're rolling IPv4, we're rolling out domain name services, because everybody's computer before that had to know about every single other network out there before they could communicate with them. And they finally say, we can't keep this updated. All right. So I gave you the precursor. Some of that's in these slides. Some of these slides I'm going to go through fast because there's a lot of there. What is a network? It's a set of devices, hosts. We're calling them hosts, connected by a communication medium, able to share data through transmission over the medium. The wires, fiber optics, wireless. Okay. I really am not enjoying the slides this way. I guess it should be okay, but I don't know why it's showing it differently today than it was last time.
Are you on like a full screen?
I am in. So let me stop share until I can figure out what the
button represent live.
Oh, you're opening up to the.
Oh, yes, that's what happened. Okay. Let's get rid of that. No wonder. Why it opened it that way, I don't know. Let's see if it actually lets me do this. There, you know, I feel more comfortable. All right. There are some of the things I was talking about, physical properties of the communication signals, physical topology of the communication medium. Like, where do the wires go? How are they connected? There are ring topologies and star topologies and others. And the logical organization. You know, if there's a hierarchy, who do I talk to? Who does that hierarchy talk to, et cetera? There's the format and timing of the signals that we get. Error, flow control. So error control, hey, what if there was a mistake? Something happened, electromagnetic interference, jamming, static. You know, you get something, it's like, that's, how do I know that that's a bad message? If it's a bad message, how do you let me know? If I sent you a bad message, how do you let me know I sent it so I can resend it? Flow control, what if I'm talking too fast? I'm sending you a whole bunch of information, you're like, slow down, my computer can't handle that. You know, connection management, how do I connect to your computer to begin with? How do we terminate that cleanly? Recovery, security, all these features are put in there and you're starting to think, that's got to be a lot of information. And the answer is, yes, it is. That's why we have standards, so everybody does the same way, the same thing the same way. Why do we use network systems? Well, to share resources. Maybe share a printer, so not everybody has to have a printer in their room. Share disks or tape drives, computational power. I can go out to the cloud and execute things there. You know, I can share a data set. Permit distribution of workload. Everything doesn't have to run on my computer. Everything doesn't, you know, there's so many cloud-based solutions. I do something on my phone and it's running off there, some data server somewhere actually doing the work and doing the computation. Google, I do a search. The search is not on my desktop. It's over on somebody else's server. A single search query, it takes enough power to heat a cup of coffee. All right. And fault tolerance. What if something goes down? Google has backup servers. One of their servers goes down, they have multiple other servers. United Airlines has multiple servers, and one of their servers goes down, another one is there. When we have a network connection, I go out and say, hey, talk to this United Airlines server. It goes to the one that's open and available. There's a load balancing too. It may go to one that's in San Francisco and somebody else out east may go to one that's in New York. And they can do that because they're connected. We want to simplify the transfer of information, database transactions, email, network distribution of data, whole lot of different things. You can think of a billion things we want. We want to be connected. So how do data networks work? They communicate over the shared medium according to agreed upon convention, a standard. There are several sets of standards out there. The Department of Defense, US Department of Defense created what we call the TCP/IP standard. We'll talk about what those are. The International Standards Organization created the Open System Interconnect model, so the ISO/OSI, just to mess with your brain. It adopts basically the TCP/IP model as the part of it. When we teach networking, we also usually teach the ISO/OSI model. Most people don't use it. Most people use the standard TCP/IP model. There's commercial models out there. Proprietary, a company can create their own networking model. Okay, I'm going to briefly talk about the ISO/OSI 7 layer, but really, actually, the emphasis will be on the DoD one. I'm not going to talk about the commercial or some of the other ones. They're out there, they exist. A lot of them deal with the lower layer of just how do we communicate. There's token rings and other things as opposed to TCP/IP, but we won't worry about that, or Ethernet. Okay, so the DoD model, it's a hierarchical arrangement of entities that communicate with peer entities in another system. I'll show you some pictures of this later. One entity within the system provides services to other entities and also uses services of other entities. What am I talking about here? I'll show you a picture. The DoD model places the importance on the internetworking. Now I keep saying DoD, I should explain this. This was the Defense Advanced Research Project Agency, DARPA, in the 1970s that put this together. The reason for this, the initial impetus of this was, besides it was cool to be able to send data between two computers, which we did, I believe it was the same summer that we had the first moon landing. We actually successfully sent data between two computers, networking. So 1969. Here was, what if there's a nuclear war? What if one or two of our military bases were taken out in a nuclear strike? Could we still communicate with each other reliably? Can we have our computers talking to each other? Can Washington, D.C. still talk to NORAD, in Cheyenne Mountain or whatever, if the main communication path they normally had was nuked? Could there be a reliable alternate path? Can we have multiple alternate paths? So let's make it basically an anarchy out there. Let's have a non-centralized system to communicate. As long as there's one network, one wire somewhere between me and the end of the world, we can get there. And let's make this reliable so it can adapt and change. It places equal importance on what we call connectionless and connection-oriented systems. I tell people, think of this as connectionless is kind of like a text message, an email, a physical letter. I send you something, at some point you get it and you respond. Connection-oriented is live, it's a phone call, it's a Zoom session, it's whatever, we're continuously being connected. And there's different things that happen when you do those. Okay. The ISO OSI model, they say the communication functions are partitioned into a vertical set of 7 layers. Again, I'll show you pictures, that'll make more sense. Each layer performs a related subset of functions required for communication. Each layer provides services to the next higher layer, while depending on the next lower layer. Again, this may make sense when I show the pictures. But the whole idea is, this is typical computer science. Let's decompose the problem into a number of more manageable subproblems. Layering is a great thing. We're going to do abstracts. I will do things at a lower layer. Once I've solved that problem, anybody at a higher layer can use that. I'll have a common interface. So where's that picture? There's my picture. So what we have in the ISO model is these 7 layers. We have what we call the physical layer, and I'll talk about the details of each of these, but this is, how do we actually get an electron? How do we get ones and zeros between the two machines? How do we physically connect them? Wi-Fi or wired, what are the characteristics of this? The data link is then still between 2 exact machines, just 2 machines that are physically connected to each other or sharing a common medium, wireless or other things. How do we turn that ones and zeros into a collection of data? And how do we control which machine, if there's more than one machine on this shared medium? Like if we have, when I came here, we had coaxial cable and drops out of the coaxial cables into everybody's office. So I could see what's going on. I could, if I wanted to, see the messages going to every other computer on that network. So how do we control that so I don't? How do we get it just to me? What if my machine and the machine next to me wanted to send information at the exact same time over this exact same wire? We're going to have collision. We're going to have congestion. So how do we control that? So the data link layer deals with all that. And some basic flow control, because again, when 2 machines are talking, one can talk too fast. The networking layer then says, okay, finally, if I have 2 machines that can talk to each other, can I chain them together? And have my machine talk to your machine, talk to his machine, talk to his machine, talk to her machine, talk to his machine, talk to her machine, et cetera, until I can get that message out across the world. So what we do is we run stuff on the machines on parallel. So each of these is a different machine. So if this machine's network want to talk to this machine's network, it sends a message. It basically asks its data link layer, hey, I want to send this whole message, what we usually call a packet of data, to this next machine. It goes, okay, let's package it up and send it out over the Ethernet. So the physical layer actually sends it physically over to this one. This grabs that data and hands it off to this data link layer software, which says, oh, I've got that. That's for internet stuff. So hand it up to the internet layer, who then says, okay, now I know what to do with it. That's not for me. That's for the next guy on the chain, and does some processing and sends it back down. And it goes up and down until it gets to the destination. So the network layer uses the data link layer. It doesn't know how to talk to the next machine, but it knows the next machine's address. And it tells the data link layer, get this to the next machine. The transport layer now takes that a bit further and says, I want to send a whole video. I want to have a streaming Zoom session or whatever. So it goes to network layer. So I want to talk to this machine way over there, the server, the Zoom server. You deal with this with me. Here's the data I want to start shipping. And the network layer says, okay, I can deal that for you. And so the transport layer only worries about what it does, which is, I'll talk about this later, but it's reliable communication. The connections and everything, but it doesn't worry about how to get the message there. That's up to the network layer. And the network layer knows some of it, but leaves other parts of the data link. So it's break down the problem, subdivide and divide and conquer. You know, the session, presentation, application layers deal with more complex recovery control and other things. The ISO model has these three. A lot of applications highest layer will talk directly to a transport layer and ignore these other two, or they'll implement these as part of the application. I want reliability, I want flow control, I want error control, I want recovery. If the network goes down and comes back up, I'll deal with it. There are some tool suites, some libraries out there that handle that for you, but it's not as standard. But the ISO people thought it would work. All right, so I'm going to go back a couple. Actually, that's what I just said. That's what I said. Okay. So a little more detail. Physical layers responsible for defining the method of transmitting bits of information, ones and zeros, across the medium. It includes the mechanical, electrical, functional, and procedural specifications. You know, what pins, how many pins, what physical size are they? What are the voltage limits? You know, you've got Ethernet cable. You got phone jacks. I don't even know how many of you ever actually physically touched a phone that's plugged into a wall. But there's, you know, phone jacks, and there's a standard or a standard jack that, but there's the I can't remember the numbers now. The standard phone one, it's two twisted pairs. What?
Is it RJ45?
There's RJ45 is the internet one.
Okay.
I'm trying to, which is bigger and has more cables and wires.
30 is enough.
The one's RJ11.
RJ11, thank you. I knew it was an RJ, I just couldn't remember. You know, but it only has like 4 wires where the Ethernet one has 8. And it's a different size plug. And then the how the wires are wrapped to prevent signals and the strength of the wires. There's different categories of wires that allow different speed of transmission. So you have the Cat 3, Cat 5, Cat 6, etc. The higher the number, the faster it can transmit data, the more reliable, because the more rugged it is with respect to protection against any electromagnetic interference. All that's in the standards. Lovely. Wi-Fi, same thing. You know, what are our modem standards? How do I communicate? What frequency? You know, and the communication channels and other things. So that's all in the physical layer. Data link layer responsible for managing transmission of information across the single link. Tends to add reliability, flow control, and error control, and communication management. Now, it could be the Wi-Fi standard, the Ethernet standards can roll these two layers together and say, our standards are talking about both of these, because in reality, we don't just want to know how you get ones and zeros. We want to know how you get a full communication packet and how you exchange information and set up that connection. So although we have these as layers, often they merge them when they implement things. The network layer is responsible for providing communication between two computers, two hosts, across the communication network. It provides interfaces such that higher layers need not know about the underlying topology, organization, provides connection management, routing. Okay, routing. I didn't talk about routing yet. Let me go back to I'll talk about it later, but let's see. Oh, gosh, it's blank. I got a computer here that wants to talk to a computer here. Well, that computer talks to my gateway, which talks to a border access gateway, which talks to this one, which talks to this one. But in reality, there's these, out here and this one, and this talks to a thing, and this talks to something, and maybe there's redundancy and reliability, and there's a whole bunch of computers over on this network. How do I know which way the message goes? You know, does it go this way? Does it go straight?
Is it just?
Does it go both? Right? And so routing is what makes us decide when I get to here, which path do I take? Which route do I take to get the message eventually here? And it depends on a lot of different things. Is there actually a connection? Which connection's faster? Which connection's cheaper? Which one's less crowded or congested? And we have different routing protocols out there. We have our border gateway protocols that allow us to figure out, you know, where these all go. Now I say border gateway protocol, basically the edge of my local area network is my gateway. And that connects to the wider network map of where things talk to each other. And it's this wider network map that I have to worry about. Now, I say that, where's my, what I'm going to do for most of this class is I'm going to have Alice wanting to talk to Bob. And I want them to talk over the internet. And the internet has been going to be this amorphous, drawn like a cloud. I don't care what it is. You know, it's a bunch of things out there, and we communicate through this cloud. Okay, that's the way we've drawn internets for decades. That's why we use the term cloud computing. Because if the computing doesn't occur out here, but it occurs somewhere hidden in this network, in this cloud, that's what we deal with. Okay, so actually that's where the term came from. So believe it or not. And you can say, no, I don't believe you. You'll fail in the test, but okay. Transport layer provides reliable end-to-end communication between programs, processes on hosts. His network layer says, my computer talks to your computer, my phone talks to the server. Transport layer says, this app on my phone talks to, or the web browser on my computer talks to the web server on that computer. And so that steps it up. Now, how do I know which application's talking to which? We'll deal with that. And it hopefully ensures error-free delivery. So the network does what we call best try delivery. It's a best try network. But it's usually connectionless. I will package up data. I will collect 128 bits, 1,000 bits, 2,000 bits, and I'll into a packet. We'll talk about what those are. I'll ship it out from the network, and then I forget about it. But if I'm sending a movie's a lot bigger than that. The next part of the movie, I package up to another packet, I ship it out. The transport layers, and as it's shipping out, the routing protocol say, no, you know, I sent this last one this way, and I got told that path is a little slow, so I'm going to take a different path to your network because we got multiple paths. So it sends on a different path. And the second part of that movie comes first. So transport layer is responsible for, well, I'm not going to give that to the application yet until I get the earlier part, because you want to see your movie in order.
Is it the presentation layer that puts them all back together?
Maybe. Typically, so the transport layer, depending on how it's done, often does this. So TCP does this. UDP, which is a datagram non-connection oriented, doesn't do that. And actually for streaming, we use UDP, and a presentation layer puts it together. For things like data transfer, if I'm downloading, we'll use TCP, and it puts it together. Because TCP is a little slower. And actually streaming, the nice thing is, okay, I got your packets, I'm missing one. Well, we'll just put a blip on the screen. We'll send it, we'll fake it. And you'll get a little static on the screen, or little, what do you call it? Pixelating, you know, where the quality isn't as good. Because they'll say, well, I'm showing you what I get in the order I get it. And if things come out of order, I'll drop them. Downloading a movie, I don't want to drop anything. Downloading a Word document, I don't want to drop my book, you know. I like to read every word in the book. Zoom, I don't care if there's a small blip. Audio, small static, I don't care. So yeah. All right, let's see. Whoa, how did I get to the end? Oh, shoot. Yeah, suddenly I got to slide 69. Oops, I lost my share. Okay, let's see that one, that one. Session layer, we can control flow of information, the dialogue between end users, grouping data, checkpoint of error recovery. That happens if the whole thing goes down, the whole connection goes down, and then it comes back up. If I'm downloading a 4 GB movie and I get partway through and then something goes down, I don't want to have to restart. It's much easier now than it used to be to do that. I did my dissertation on a 1200 baud modem. That's 1.2 kilobits per second. What I wanted to, I created a PDF of my dissertation, which is about 130 pages, and I needed to send it to campus to print. So I log up on my modem and send it, or I put it on a floppy drive, bike to campus to print it. Well, guess which way was faster? My biking. And I was a mile from campus. Okay, presentation layer manages syntax of data being transmitted, conversation between two different formats, different representation. We have virtual terminals, we can do cryptography, we can, handle the ordering and things. Like I said, session presentation layer are often combined into the applications or into libraries of the applications. The application layer is the final management function, support the programs you're actually running. Okay. Like I said, we go into much more detail in this in the advanced class. I've just given you an idea. This is there. So the DoD layer, developed in the 70s and 80s, we have the 4 layers: the process layer, host layer, internet layer, network access layer. Network access layer kind of rolls together the logical, the link layer, and the physical layer of the network. So we have our device drivers, network adapters, all those. They, like I said, they often combine it into one. Internet layer is the network layer and ISO, so they're the same thing. I will talk about this a little bit later. Host-to-host layer is the same thing as the transport layer and the ISO. Process layer is same as the application layer, and includes typically presentation and session, all that. So most people deal with it this way. But we may call, and they'll call it, what's interesting is we'll say this is the physical and logical link layer, this is the internet layer, this is the transport layer, this is the application layer. So they'll use most of the ISO naming, except for this one, they'll call internet. Why? Just because that's the way it is. So what's important here to understand is for any layered network model, encapsulation is key. For example, say I want to do a web request. That's the protocol, the communication protocol that allows my browser to talk to your server is called HTTP, Hypertext Transport Protocol. I think I'm missing something. No, that should be it. Correct. So I make a request, get me this file, this image from your server so I can display it in my browser. So it talks to the transport layer and says, hey, transport layer, I need help. I need to talk to the server over here. I need it to give me information. So it says, okay, here's your request at this higher level. I've got your request. I'm going to copy that request over because I don't deal with that. You also gave me some additional information, like what machine you're talking to. I'm going to put some of that information I need into what we call a header. So the TCP header tells me which application on my machine, my client, my browser, which application on your machine, so your server, and some other things to, ordering and sequencing and everything, and puts that over this so that the transport layer on the other side can get this data and say, oh, I know who to give it to. I also usually put additional information that I pass in that's not included here that tells it, hey, what machine I want to talk to. That gets included in the internet protocol header. Okay, this is who I want to talk to. This stuff is all just encapsulated and sent there. The internet protocol then passes a lower level. So if, for example, I'm using Wi-Fi, we use the point-to-point protocol. or on my router, whatever. So that whole thing is encapsulated to send from one machine to the next machine. And I say encapsulated, I drew it on both sides because usually not only is there a header sent in there, there's usually some trailing error check codes. So it's stuff on both sides of the message. So I say a header in this, basically it's a sequence of bits, ones and zeros, or a sequence of characters, however you want to call it. Starting from the left, we usually look at it going to the right. So this is the first part of the message, like a get message would be GET, and then the rest of it in here. This is how the network model works. Now, let's say I do a remote login to somebody, or even I'm logged into Amazon, I start typing stuff. Or I like the remote terminals even better, okay? The remote terminal example, if I do, I did that before where I logged in, was showing you OpenSSH, for example. So I can log into another server. You do this if you're taking the CS programming class. And I start typing commands. Each command's a keystroke. When does my machine send that to the server?
When you hit enter.
When I hit enter, but sometimes I hit a single keystroke, an up arrow, back arrow, and I need that server to respond. Right? So sometimes the program, my program decides which way to send it. Sometimes it just says after a certain amount of time, I'll give you 40 milliseconds, give me as many characters you want, then I'm going to send them. 20 milliseconds, whatever. Okay, TCP header is typically 20 bytes. Oh boy, I can't write here. IP header is 20 bytes. A single character stroke is 1 byte. If I type slowly, it's sending 1 byte at a time wrapped by 40 bytes. It's a horribly inefficient mechanism, but hey, that's where we are in the world. Okay. Then, so it gets to the far end, actually each intermediate host decodes what it needs. So the internet layer takes the IP header, looks at that at the next host and there says, hey, that's not me. I know how to get it to the next place. Wraps it up in a new PPP protocol packet or whatever, packet, Ethernet packet, whatever, to send it to the next hop. And says that's the next place to go. So we build this, unbuild this, and finally we get to the destination. It says it takes the TCP header and packages up all that information and sends it up to the application. The application can usually see this information too, or ask the operating system that delivered this, who did this come from? Give me some information. One, if I'm a server, I get a request, well, who do I respond to? What application on which machine? So give me that information so I know who to respond to so I can build up the response. So just think about that. All this has to go into how we build this. And then start thinking about how do we prevent somebody from lying? Bad guys lie, cheat, and steal. Remember that. So you send a message, how do I know it's really from your computer? What if you sent a message pretending to be from her computer? Who do I respond to? Her. What if you sent the message in a way that my response to her looks like I'm asking her to do something for me because she's running a server? She's Google. She's running the Google server. You send a request, I send it to Google. Google does some work and waits for me to respond. Oh, by the way, you didn't just send it to me, you sent it to him and him and him and her and him and him, and everybody responds to Google. And Google thinks all of these people are connected to him and tries to do all these things. You can do what we call a denial of service attack by overloading that server by sending all these fake messages. And there's lots of different attacks for sending these fake messages and tricking Google into doing things. And we'll talk about some of what happens there and why. Okay. Those others are more complex attacks too, if we can avoid that one. So back to the big picture. Internetworking, again, how does this all work? There's some major issues. We want to provide a service. Networks attached to an internet. So my local network, WSU's local network, those networks are attached to an internet. How do we work internally? How do we communicate with computers inside? Some of those could be connectionless only. Some of them could be connection oriented. How do I establish what I'm doing here compared to what they're doing here so we can communicate? And networks, we have to normalize that, provide a standard interface. So over the internet, it comes in looking the same. And then internally we decide, okay, that gets translated this way for my type of network, that way for your type of network. Wired versus wireless, we're going to translate it differently. They may have different delay rates, error control mechanisms, maximum packet size. Again, packet is the amount of bits we're sending at a time. My network to say, hey, you can do 4,096 bits at a time. Your network says 1,024. My 4,096 shows up at your front door. What do? Well, you're going to break it up. You're going to segment it. You're going to take that packet and break it up into 4 pieces and then send it on. Well, you weren't in my destination. You were partway through. You hit another one. The packet size is 512. So it breaks everything up there. Then finally, at the end, it gets back to somebody. It's only at the end do they reassemble. But how do we know that this packet, I didn't put all that information in there. How do we know how it got broken? That has to be dealt with. How do we have you tell me I can't deal with it anymore? Stop sending me data. My gateway is going down, my router is going down, you got to send it somewhere else. How do we tell me that? And so there's a whole protocol out there called the Internet Control Message Protocol. Lives at the internet network layer, but actually uses IP to send responses back, where an intermediate agent or the end agent says, hey, that's done. We can't do that anymore. How do we do addressing? The network point of attachment is a unique network-wide identifier. That's our 129.101.100.1 type address. Internally, the naming may be different. So we had to do that translation. You know, we need inter-network-wide addressing and name resolution. And the name resolution came into, why don't I call it google.com and find a way to do that and translate to an internet-wide address. So Google actually can have both an IPv4 and an IPv6 address if I'm using version 6. Routing. So I'm going to have an end system, my host. It's going to have a network address. And we're going to have intermediate systems. Something between my host and the final end host I want to talk to is an intermediate system. Could be what we call a gateway. Gateway connects my local network to the external network. And there may be intermediate gateways in there that route. So I used to have a good map of this. We would have a connection from here. We go from here, let's talk about the slightly older version, to WSU, to Spokane, to Seattle, to San Francisco, and then out to the world. Right. And so there'll be a fiber optic cable right now from WSU all the way to Spokane, from Spokane to Seattle. And so, but at the routing point at WSU, it'll decide, okay, do I send this up to Spokane or do I send it? We now have the Idaho Regional Optical Network, so it's fiber optic network within Idaho. And so my message actually could say, hey, it's actually faster for me to go through Boise. And from Boise over to, I don't know where Boise would go, to Salt Lake City, from Salt Lake City to San Francisco, and then up to Seattle, then through WSU to Spokane to Seattle, and that's okay. But we'll have different machines at each of those cities I'm mentioning, probably several of them, that make these decisions. I'll show you that later because that's kind of cool what it looks like. So my end system, is there more than one intermediate system I can talk to? One intermediate host, one gateway I can talk to get out there? How do I decide which one? Even if there's only one, how do I know which one? What is my gateway? Who do I talk to? You know, on my machine. Oh, I lost that window. So if I'm running on Windows, for example, if I do IP config, Internet Protocol config, it tells me this is the Internet Protocol address of this machine. Here is its default gateway. That's the address of the machine that I talk to get out of my local network, this building's network. So I talk to 129.101.95.1. I'm machine 25 in this network. Here's my link local, so my Ethernet IPv6 address. So that information's in there. If I do /all, it gives me more information. Yes.
Doesn't the IPv6 address look a lot different than the IPv4s?
Well, so IPv6, yes, looks a lot different. Looks like that,
Yes.
as opposed to this, because it's a whole lot more bits.
Okay.
So this one, I don't know, can you see this okay? Do I need to make it bigger? Okay. There is DNS, or those are the name servers. There's two of them, 129.101.119.223 and .220. If I say, hey, I don't know who www.google.com is, I say, oh, I'm going to send a DNS, the name service request to that server, and that server will figure out the information for me. So that's where that is. This is my default gateway. Okay, I have an internet protocol number. I haven't talked about this yet, but I'm just let you know this. How do I get my number 25? I'm 129.101.95.25. How does this machine know it's 25? Either I can hard code it in when I set up the machine and say, hey, your number one this, or I can say, I'm on a local network. Somebody out there give me a number. So there is a domain server, and the domain host control protocol, DHCP, is the one that gives me the number and says, hey, here's the number you're using. And I'm now going to bind your MAC address, your actual MAC address you have, which is up here, my physical address, my 00D8615D6C EB number, with 129.101.95.25. And the world's now going to be, when you're communicating, I know this, when it comes into our gateway to 129.101.95.25, it says send it to this MAC address.
Is it unique every time you start a session though?
So now I'm going to get to that. In here, you can see there's a lease. Lease obtained Tuesday, October 12th at 3 a.m. Lease expires Wednesday, October 13th at 3:30 a.m. Lease is how long I'm allowed to use that IP address. I go out and ask DHCP, it comes back and says, here's your number. Good for a day. Now, there's ways I can release it and renew it and ask for it back. If I was a server, if I was a printer or something else, I don't want that number changing every time. And so the DHCP server, we can reserve and say, hey, for this MAC address, always give them the same IP address, because we don't want to change it. And it depends how it's configured. The one in my office, I turn it off, I turn it on, it still always has the same IP address. It's not a server, but we've configured it so that it always has the same IP address, because some of the research I do needs me to know it. The one I have at home connecting to the internet, no. So I can't run a server at home and have people always connect to the same IP address. I have to have a different mechanism of doing that, which I have. Well, actually, when I had a small consulting company, I did that from home. I didn't do that. So that would be what you call static IP address. It's always the same versus dynamic, where it changes. So, and dynamic host control protocol, domain host control protocol, whichever does those. So these things are out there. I'm just letting you know they're out there. We're going to go back and look at some of these in detail and how you would set them up and use them, but just letting you know these things are there. Okay. Go back to the slides. There's also things in there called quality of service. Delay costs, security, cost limits, residual error rate, priority. If I want high quality service delivery, high throughput, everything, I'm going to pay more, basically. Quality of service. I love this. The quality of service was designed to allow you to pay more, or allow the service provider to charge you more. So when it goes out to the intermediate gateway and says, oh, I can go on the iron network, I can go through the traditional WSU network, what gives me better quality of service? I should say it was really fun back in the mid-90s when we had a connection just from us through WSU, through Spokane to Seattle. When Microsoft, quote unquote, discovered the internet, when they figured out, hey, we need to set up internet services and do things, and they set up web servers and everybody started doing things, our connection to everything past Seattle dropped to a crawl, because we had to compete now with everything Microsoft was doing. The whole Northwest complained, and Microsoft bought their own private link then to San Francisco, because they were shutting down the whole Northwest internet. Now, speeds, So my home, I have a gigabit Ethernet at home. You know, you hear enough about the speeds, I guess you understand. When I first got here, we had two 56K, not megabit, not gigabit, kilobit per second modems from campus to the world. One from the computer science department, one from the rest of campus. We then upgraded to what we call a T-WIP1 link, which was a megabit per second, which we shared with WSU. We're way above that now. I don't know what the connection is. It's much higher. When I moved here with that 56K link, I was trying to download stuff from UC Davis over that way. I should have waited. All right, maximum packet size. Again, I talked about this. And this is affected by your error rates, your transit delays, buffer limits, processing overhead, etc. Anywhere from 128 bits to 65,535 bytes, 128 bytes, 65,000 bytes are typical, depending on the protocol. Why 65,535? 2 to the 16. Each network has maximum specified for transport layer to divide into transport protocol data units into segments. So I talked about the TCP thing, and it was packaging stuff up, right? Something with a single TCP header and all the data it's sending is a protocol data unit, a packet for that protocol. So that'd be the transport protocol data unit. Then the next layer down would be a network protocol data unit, which will be the IP header with all the data it's sending. Okay, there's flow and congestion control we have to worry about, and error reporting. I realize I've got duplicates of some of this data later, so let's talk about the internet protocol. I want to explain this first because this becomes important. RFC. RFC actually stands for request for comments. So the Internet Engineering Task Force, the IETF, manages and standardizes everything that goes on the internet. When you're trying to create a new protocol, make suggestions or change, you put together a document called a request for comments, and you send it to the IETF. If it's a proposal for a standard, what they do is they review it, and then it goes through several different layers before it becomes a finalized standard. They never rename it. So the Internet Protocol Standard is defined in RFC 791. Now, if you actually, so you see here, it says IETF.org. If I click on that, it will actually pull open the standard, which you're going to hate me for this, but and it was 1981, and you can tell this is a horrible text-based version, pure text, and it's hard to see. But this is the standard. It talks the introduction, the motivation, scopes, overview, the specification. If I go to the header format, there's the wonderful graphics from 1981 that showed you the Internet Protocol header format. Okay, because everything's ASCII text, but it worked. Okay, we'll go back and look at these. This is where I'm getting stuff in this next part, is from this standard. This is standard 791. I think the most recent standard is over 10,000. RFC, they're up there. There's a lot of these, but certain you should say, oh, I want to know how TCP works. There's a standard for that. I want to know how email works. There's a standard for that. I want to, you know, there are standards for them. And when you write applications, they have to follow those standards. All right, let's go back to, so in the standard, they talk about the motivation. Why did they create this? For interconnected systems of packet switch computer communication networks. Again, packet switches, you take a chunk of data, you send it out, it gets switched between different machines on different connections, but there's not a single connection. Where they compared that to circuit switch, where basically I say, I want to talk to your machine. Here's my, from me to this machine, to this machine, to this machine. We're going to reserve that link and only I'm using it. That's how phone calls used to work. Where you actually had the switchboard operator connecting, oh, you want to connect to them? I'll connect this cable to this cable, that's you. And when you're done, I'll disconnect that circuit so somebody else can use it. but I had so many lines between my site and your site, and everybody would reserve that circuit. Packet switches, I'm gonna send this packet of data and then I'm gonna make it immediately available because you're not constantly talking or you're not talking fast enough to take up the whole thing. So the next packet can go along and share that same link. And they now do that with modern phone systems because everything's digitized. Okay. So the internet protocol provides for transmitting these blocks of data. They call these blocks datagrams or protocol data units. Okay, but the blocks will, so you'll hear the term datagram from source to destination. It's specifically limited scope to provide the functions necessary to deliver a package of bits, a datagram, from source to destination over an interconnected system of networks. No mechanisms to augment end-to-end data reliability, flow control, sequencing, or other services commonly found in direct host-to-host protocols. We're going to deliver it, we're going to do a best try, but no guarantees. The internet protocol can capitalize on lower level services as it's getting it across there and hopefully get everything with good flow control and reliability and sequencing, but no guarantees. The protocol has a standard set of interfaces that the higher level stuff uses. And it calls on local network protocols to carry out, calls local ones to carry out its services and get that datagram across. So that's the scoping, that's the plan. You know, and like I showed here again, so I can have different application protocols, Telnet, that's remote login, SSH is more common now, HTTP, hypertext file transfer protocol, email, other things up here. They'll use these transport layers, which will use the internet, which will use the local networks. That was the goal behind it. Addressing becomes a really, 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 really important part of this that you need to understand if you're doing cybersecurity. And I'm going to come up with some more tutorial stuff about the addressing because this is not the best for you to look at, okay? Typically what they defined in the initial standard was that we could have different classes of networks. All network addresses are 32 bits in Internet Protocol version 4, broken up into 4 8-bit parts. Those 8 bits give you numbers from 0 to 255. Typically is how we read them. So class A networks are ones where they get that unique top number. Okay, it's a 7-bit number. So there's 128 of these. The very top number is a 0, the top bit. So out of your 8-bit number, the first bit is 0, the rest we can change with things. Well, that gives us everything from 0 to 127. If that top bit was a 1, that gives us 128 up. That's why U of I is at 129, because we're not a private class A network. So anything that's below 128 is going to be part of this private network. Okay. Class B, that's more corporate wide, you're going to get 16 bits. So that gives them 16 bits, 65,536 possible addresses. The top 2 bits are reserved, they're a 1 and a 0. So that's the numbers from 128 through 191. Because 1 would be a 192. 128 plus 64 is 192. So that's why we're 129.101, because we fit in there. Class C, single small LANs, have 21 bits of numbering. And so, and like I said, I'll show a better tutorial of this, but basically, if we have our numbers, you know, here we have 0 and then a bunch of numbers, 1, 1, 0, whatever, 1, I can't do that. There's 8 bits here, and then the remaining 24 bits are up to them to play with as they want. When we come to the U of I, so we're at 129.101. I can't show you that. That's 16 bits. The bottom 16 bits are up to us. So we have up to 16 bits, 65,536 possible devices that we could use at U of I. Class C would be a smaller network, and we'd be like 129.101.42. Okay, or 192.168. That'll look familiar for anybody who has local addresses. And Class D is really low. Okay. There are lots of ways of doing this when we deal with networking that I need to, like I say, go over a tutorial with. Because this assumes the 24 bits. Well, this has a 21-bit network ID, and the bottom 24 bits are for hosts. I could actually subdivide my campus network further. And I could say, actually, I'm going to not use the whole 24 bits. I'm going to use 18 of them, 12 of them for a local network with a building specific network. And I'm going to have another 12 for another building specific network and break things up further. And there's lots of ways of doing that. That has to be understood when you're configuring networks, because if you don't do it right, you're talking to the wrong people. You do it right, you can also prevent who's talking to your network, and it's a security thing. I can isolate and limit how many devices are on my local network, what the possible addresses are, and then when messages come into the wiring closet, it says, oh, that doesn't go to this room, that goes elsewhere. Configuring these all correctly is non-trivial. And you can use DHCP and say, hey, you decide for me. I don't want to know this. Or you can actually go and do it yourself. The problem is, let's see, was this in there? Darn, they didn't show me that one. I was just, it's not in that one. Okay, I'll have to figure out how they show that there. The problem is I own my computer. I have control over my computer. Because I have control over my computer, I can lie and I can pick whatever network address I want. Most computers also allow me to modify that MAC address, though you weren't supposed to be able to. We can do that. So that gets us some security problems. Because here's one thing that happens. My local network, it comes out, it says, hey, I just got a message for 129.101.95.25. I don't know who that is. Hey, who owns this IP address? My local gateway will send that message out to everybody in its domain of control, waiting for a response. My machine will respond, hey, I own that. Now, maybe it'll talk to the domain host controller, but maybe it'll just ask me. Well, I responded, but you saw the message too. You respond, I own that. Which response does it get? Which one does it bind? Because now the next message that comes in, it says, I know which MAC address owned that. My message in that Ethernet wrapped, that lowest level link layer protocol, I'm not telling you which IP address is getting this. I'm telling you which MAC address is getting this. So I add that that Ethernet address. So when it comes out over there, you look and say, hey, that's me. That's my Ethernet address. I'm going to grab that message. And so you can own multiple IP addresses, and they all come through to you. And then you get that Ethernet message. You say, that's me. Now, because you own the machine, you can also say, hey, I see that Ethernet message. That's not me, but I want to look at it anyway. That's called promiscuous mode, where you're able to look at whatever goes across the wire in front of your eyes. And now I'm eavesdropping and spying on everything that's on my local network. But this is how they do this, and they organize it in such a way that, so, the 129.101 is University of Idaho. Nobody else in the world owns that. Anything to 129.101.anything comes to our main gateway to the internet, and from there it comes to the right machine, hopefully. That's what we need to do. All right, I got very little time left. Like I said, they're usually represented with dotted decimal notation like this: 129.101.100.1. Local network may combine many different local area network types at the network layer, causing the routers to be used to decide, hey, I got it to this, who does it really go to? I'm going to reroute it, so router. And subnetworking in Class B help reduce workload. I will talk more about that in a bit later. All right, this is where I'm going to stop because I don't have enough time to go over this. This, though, I want to mention is the network protocol data unit, the header for the internet protocol. This is bits in order, so this is showing 32 bits wide. Okay, so this one's 4 bits. We will use a term in here called octet. Octet means 8 bits. Because at that time, not everybody agreed a byte was 8 bits. Some people had, well, I have a machine with a 10-bit byte. So octets. So we will go back and talk about this because this is important to understand for cybersecurity because this is where we got to control things. Now, last, before we finish, if you did not, I can stop the recording. If you did not pick up your test, I returned tests last time. I have them here.